Okay, great. Welcome, everyone. Thank you for coming to the CI Compass Fellowship Program's end of summer symposium. Welcome. I'm very, very excited to have our students show us what they've been working on this summer. For those of you who don't know, CICF is a fellowship program that we developed to increase the amount of students interested in cyber infrastructure, especially within the context of NSF major facilities. These students have gone through a 12-week research and technical training program where they learn skills that CI professionals use in their day-to-day lives, especially at major facilities. And this summer, they've been working at a variety of MFs. We had some at NCAR, some working on NEON projects, and some at OOI. Okay, so I think with that, we will start with our first presenter, Gareth Oram, who is a first year, is now going to be a second year in mechanical engineering at LSU.
All right, so she said, my name is Gareth Oram, and this presentation is about my my remote internship at Woods Hole Oceanographic Institution. Okay, so first off, a little bit about myself. I am going to be a second-year mechanical engineering student at Louisiana State University this coming fall. I participated in the CI Compass 2023 Spring Fellowship Program. And I have currently completed 3 out of a 6-week internship with Woods Hole. My summer got very busy towards the end, so I had to divide it into 2 separate parts. So I will actually be going back and doing the second half of my remote internship in the winter. So before I started as this internship, I had no experience with any internship whatsoever or working with any major facilities. I did have very basic knowledge of Python programming language, though. That was about it. Okay, so start off a little bit of general information about WHOI. So it stands for Woods Hole Oceanographic Institution, located in Woods Hole, Massachusetts. So they're under the Ocean Observatories Initiative to collect and store and process oceanographic data. And they maintain and operate a fleet of oceanographic equipment, including 2 large research vessels. One of them is pictured here, and other unmanned equipment like submarines and buoys. All right. So first off, takeaways from this experience. I advanced my knowledge in Python programming language. That was kind of the surface level. I became more familiar with the process of debugging. I also learned how to use .csv files in code, which is something I hadn't really done before. But on a deeper level, this internship familiarized me with working in a professional working environment. I got to work side by side with professional software engineers and experience that kind of the daily stand-up meetings and that working environment, which was actually a lot of fun, and it was really interesting to me. And so of course through that I also improved professional communication skills and just gained a lot of workplace experience, I guess, that I wouldn't have otherwise gotten. Okay, so my role at WHOI. So as I said, I am to do a 6-week long remote internship. I've already done the first 3 weeks. I did that back in June, and the second 3 weeks are still to come in December. And my supervisor was Jeffrey Glatstein, who's here today. And I was assigned a small project that kind of matched my experience with Python, and it was to help further it, really. All right, so description of my project. So I was assigned the task to build a scraping tool, I guess we called it, um, for that would it would kind of comb through data logs that I was given. I was sent two or I sent two folders full of these, very very long, just kind of raw data logs, and I'd use Python 3 programming language to create this tool. The goal was to read um, both cabled and uncabled data logs, which I'll explain in a second, and collect the desired information from them, and to then sort and store the information into .csv files, which turned out to be in the form of Microsoft Excel spreadsheets. So another element of the project was actually to scan for failures, I guess, in each log, and store those in two separate .csv files. Okay. Right, so just some background information on cabled versus uncabled data. So this was actually, well, surprisingly literal, really, in its meaning. Cabled data means that the data that you're looking at was transmitted through physical wires. So in the case of this data, the buoys that collected this data were actually tethered to the shore, and so data was transmitted that way. Whereas with uncabled data, they were collected using buoys that were connected wirelessly, so buoys floating in the ocean. And so if these buoys were close enough to the shore, that means that data would be transmitted through cell towers. But if they're too far for cell towers, then they use satellites instead, which was really cool to me. All right, so that's cabled versus uncabled data. All right, so here's just requirements for my program. So as I said, I had to read both cabled and uncabled data logs and record the desired information from these logs. So desired information included timestamps, which there are quite a lot of them. That they're very precise timestamps. Have to record the file path, but this was for uncabled data only, so I didn't have to worry about that for cabled data. I'd record particle counts, particle speed, and also total processing time, which these were all represented via numbers and certain text patterns in the raw data logs that I had to kind of observe and learn how to work with those. So that took a bit of time, but as soon as I figured out kind of what the pattern was and how to express them, excuse me, in my program, it became a lot more straightforward. So yes, then if a line of code, or if a line in the log included a failure, then all of this information would then go to a separate file, so a failure log, as well as the number of failures in that line. And so also cabled and uncabled data had to be kept separate. So because of this, I ended up with 4 separate .csv files. Two for failures and 2 for regular non-failure data. Okay. So starting the project, I must say finding a starting point was actually probably the most difficult part of this project. But I was advised to start with just simply counting the number of failures in one log, just, one file. So my first method of doing this, which I mean, technically it worked, but it wasn't very accurate, really. Was what I would do was I was told that each line in the log of interest started with the phrase particle factory, and so I counted every line that included the phrase particle factory, and I would then count the number of times the phrase slash and then a zero and then another slash appeared, because that represents a line in the log without any failures in it. So by subtracting the number of non-failures from the total amount of lines of interest, I would get an estimate of the amount of failures in the total log. Excuse me one second. So I got this to work, but what I realized was that this actually only counted the number of lines that failures occurred in, but it didn't give me an accurate count of the actual number of failures in the logs, because sometimes the failure number would be like 2 or 3 or 4 instead of just 1. So I had to I had to learn how to work around this, and so I learned how to search lines for specific text patterns, which was a method that I used for the rest of my program. Okay, so sorting data, I used if statements to check for failures first, and then as soon as I had figured out whether there were failures or not in that log, I would move on to, well, if there are no failures, then search for all of the desired data and record in the regular .csv file. But if there were failures, it would record that first and store it in the failure log. And I had two kind of almost identical blocks, one for the cabled data and others for the uncabled data. Okay, and my end result was something that looked a bit like this. So I was able to sort the timestamps, particle speed, particle count, and the total processing time into a Microsoft Excel spreadsheet with labeled columns. I've made that a little bit prettier, but that's what I got. This is an example of cabled data, because the file paths in uncabled data were very long and couldn't fit on my screen. But yeah, I ended up getting about 4 very, very long Microsoft Excel spreadsheets at the end. One of them reached about like 1 million lines, I think, which I couldn't save on my laptop. All right, again, this is my takeaways slide. And photo credits. But yeah, that sums up my experience at Woods Hole. It was a very positive experience for me. I very much enjoyed working with Jeffrey Gladstein and his team, and I'm really looking forward to going back in the winter. Again, it was kind of an eye-opening experience for how not just how it is to work at a major facility, but also how it is to work in a professional working environment.
All right, so our next speaker is Raja Ali. He is an up-and-coming second year in computer science at University-Purdue University, Indianapolis, and he'll speak to us about his work at NCAR. Go for it, Raja.
So hello everyone. It's good to see some familiar faces and some new ones as well. So for those of you that haven't met me before, thank you for the introduction, Nikki. But I'm Raja, currently in my sophomore year studying computer science with a minor in math, and at Indiana University, Purdue University in Indianapolis. This summer, I had the incredible opportunity to work at the National Center for Atmospheric Research, also known as NCAR, where our main goal was to enhance both the performance and usability of the ionosphere dynamo model. The term ionosphere dynamo model, or VACUM-X, might seem terrifying at first. Believe me, I felt the same way. But before we delve into the technical and cyber infrastructure aspects, let's build a foundation by understanding some fundamental atmospheric concepts, which will, I think, pave a way for a clearer picture of the approach I took for this project. So I would like to start by talking about the ionosphere, which is a layer situated about 62,000 kilometers above the Earth's surface. filled with ions and free electrons. So why is this layer so significant? Well, there are multiple reasons for this, such as studying the ionosphere is crucial to our understanding of Earth's atmospheric and communication systems. This layer also plays a key role in propagating radio waves, which affects global communication systems as well as satellite operations. It also responds to solar activity, which contributes to one of the most beautiful phenomena you might know as the Northern Lights. However, the ionosphere behavior is complex and can vary with time of day, altitude, latitude, and levels of solar and geomagnetic activity. Now, that's where modeling comes in. By creating more accurate models of the ionosphere, we can essentially predict its behavior, improve our communication systems, and further explore greater aspects of space weather. Now, to do this, our primary focus was to enhance the performance and usability of the ionosphere dynamo model, which is a tool that helps us study this layer of the atmosphere in depth. Now, this model was in need of significant improvements, and our ultimate goal was to make it better so that it would be easier to integrate this enhanced model into the whole atmospheric community climate model extended, also known as WACOM-X, which is a more comprehensive model used for studying the Earth's atmosphere. Now, our approach to achieve this goal involves several crucial steps, primarily emphasizing effective software engineering and cyber infrastructure principles and practices, rather than the atmospheric side of things. Now, this diagram shows the software engineering process we took in accomplishing our goal, starting from initial code refactoring as we aimed for superior adaptability and a more streamlined workflow. Then came the Fortran code transition, where we had to move from fixed to free format to boost optimization and simplify file organization as well. We also harnessed X11 forwarding and Xarray in Python for in-depth model visualization, which turned the really complex ionospheric data into clear, interpretable visuals. Now, our commitment to reliability also led us to establish a continuous integration, continuous delivery pipeline, which I'll talk about more in depth in the next few slides. Now, if you look at the video demonstration of the original code base, now some of you might be surprised by this, but there were several hard-coded, commented out absolute paths, with only one of them being used in the model. Now, this is not the best way to do this, especially in terms of usability, which was the main goal of the project. So in order to make the model more adaptable and run it in different computing environments, we had to go in and transform hard-coded absolute paths like these into more relative ones so that it could be used in different computing environments. We also introduced a nameless file, which basically allows for streamlined parameter control, which in turn enhances computational efficiency and also ensures consistent input configurations across various time steps in the model. So the result of all this was that this significantly improved computational efficiency by 117% by removing compile time. And it also enhanced parameter handling, changed the scientific workflow which the other developers were using, and also prepared the model for high performance computing on a larger scale known as exascale computing. Now, imagine having a book with no index or table of contents. Navigating it would be really, really hard, right? So we faced a similar situation with over 30,000 lines of complex Fortran code with some fixed format Fortran files and a flat directory structure. To make the code base easier to navigate and work with, we converted the directory structure into a hierarchical one, which involved a lot of changes to the makefile. Now, this would reduce the chances that the developer would introduce bugs into the code base. And even if they do, they have a clearer direction of where to look for the bugs. Also, if any open source contributor wants to contribute to the Ionosphere Dynamo model, they would be more motivated to do so if they looked at the refined structure of the project because they know exactly where to look for to improve things in the model. We also transitioned 20% of the Fortran code from fixed to free format. Now, this shift required syntax modifications to the NetCDF Fortran interface and leveraging array operations from Fortran 90. Now, the thing with Fortran 77 is that it uses a lot of do loops, and it can be really cumbersome sometimes to use the do loops. So the Fortran 90 interface utilizes array operations, so you can replace those loops, and which leads to enhanced performance sometimes. I also wanted to share this case study where in the first few weeks of my internship, we observed a non-deterministic behavior in the model's output. And both me and Brian thought that this was really weird. So what was happening was that the netcdf output file was sometimes generated, other times not, and there weren't any changes to the code base. To address this, I utilized vtune, gprof, and gptl timers for profiling and debugging. Now, this inconsistency still persisted until a critical update was made to the Intel compiler from version 19.11 to 22.1. Now, this revealed a compatibility issue between the older Intel compiler and the netcdf dataset. So what can we learn from this case study? While some problems appear complex, their solutions can be quite simpler than we think they can be. And also staying updated with software tools and dependencies is essential for consistent, accurate outputs, especially in a large scientific environment such as NCAR. Lastly, even though my approach wasn't helpful in finding the ultimate solution, it was still a good experience in learning these tools. Furthermore, we also created visualizations for the model, specifically using Xarray to extract, process, and display data from the netcdf files. So this not only enhanced our ability to interpret complex data sets and also derive actionable insights, but it also facilitated some rigorous testing, which would ensure reliability and accuracy of our computational outcomes, as I'll talk about in depth in the next slide. But before that, I'd like to give a brief overview of the visualizations. The first plot represents the spatial distribution of the electrostatic potential in the Earth's ionosphere at the first time point. So the electrostatic potential is a key quantity in space physics, as it is directly related to the electric fields and currents in the ionosphere, which are important drivers of space weather phenomena. In the second plot, the x-axis displays longitude and the y-axis displays the latitude. Now, the color variations from cooler to warmer represent geopotential levels. In the ionospheric dynamo model, geopotential affects charged particle behaviors, and so the second plot basically offers insights into the ionosphere's energy landscape. Now, building software is just like building a car. Just as a car has to go through various stages of quality checks before it hits the road, software code also needs to pass multiple tests before it's ready for use. To do this with the model, we established a continuous integration, continuous delivery pipeline. Now, this is like a quality control system that basically uses automated testing to catch issues quickly before they are pushed to the working model so that the developer doesn't mess anything up. We also expanded our test coverage through automated Python scripts and unit testing for our Fortran code, which was integrated into the CI/CD pipeline. So to implement the pipeline in the model, we explored several methods, including self-hosted runners, as well as runners provided by GitHub Actions on their Ubuntu server. So for the first approach with the self-hosted runner, while it is much easier to set up the pipeline through the self-hosted runners, it was, I guess, really less user-friendly because each developer had to go in the GitHub Actions set up their own self-hosted runners because of unique permissions on the supercomputer Cheyenne. And then they also had to run a script before pushing to activate the pipeline on the self-hosted runner. And each developer had to do this on their own. So this wasn't necessarily really user-friendly. So we utilized the Ubuntu servers provided by GitHub Actions, which is available to each developer. But the problem with that is that it is really hard to replicate the same environment of Cheyenne, the supercomputer where the model was running, into the servers. So we had to go through the process of using Docker, a tool that packages software together into standardized units, and use Docker containers and the process is shown here where we loaded all the modules into the Docker container, and then they were pulled into the CI/CD pipeline, ensuring that the pipeline runs, and any developer that pushes to the code base could now run the pipeline. So the two screenshots highlight the pipeline variations. One utilizes self-hosted runners, while the other uses the Ubuntu server provided by GitHub Actions. Now, focusing on the test model aspect of the pipeline, we integrated Python scripts to validate the L2 norm difference between variables in the generated netcdf file, ensuring that they met a specific criteria. And if they don't, then the developer is notified that even though the model runs, they might have introduced some bugs in it if the difference between the variables is exceeding the tolerance level set in the Python script. Additionally, this step also introduced unit testing within the model because there wasn't any unit testing before, and it also adds the basis of expanding unit testing in the future. And just to clarify, we use PF unit for the unit testing in the model. Now, building on the test model step in the pipeline I touched on earlier, I wanted to include the last case study from my internship, which Allison, one of my mentors, recommended to add. So in our model evaluation, the variables potent and potent test, which represented electrical potential, stood at center stage. Now, our goal was, after establishing the script for testing the L2 norm, was to establish a solid benchmark or tolerance for these variables against potential future tweaks. From our initial findings, the L2 norm difference was around 0.208, greater than I thought it would be because I remember setting the tolerance to 0.01 in the Python test script. And so after setting the Hall conductivities to 0, we noticed the L2 norm difference decreased to 0.05. And our roadmap ahead includes zeroing in on an appropriate L2 norm threshold so we can further dissect the potential impacts of modifying other variables as well. Now, what we can learn from this case study is that even though the L2 norm decreased, the scientists, specifically Astrid from HOA and NOAA, questioned whether this would be enough. And sometimes in research settings as these, we have to do a trial and error before deciding a tolerance for tests like these, which even the scientists aren't sure what it should be because for such a complex scientific model such as this. Now, that was all I accomplished during the project this summer, and the refined model now opens new avenues for more accurate and comprehensive atmospheric studies, making it easier to integrate the whole atmospheric community climate model extended into the ionosphere, converting the ionosphere data model into WACOM-X. Now, future goals of the project include integration of GPS support and NPI-based parallelism because the code was completely serial and we weren't utilizing any parallel processing in the code base. Now, this would further enhance computational efficiency, handle larger data sets, and streamline the model for scalability and also advanced atmospheric research. And at the end of my internship, I had the opportunity also to present my poster at the 2023 NCAR Summer Student Research Poster Symposium. So, and for a clearer view of the poster, you can scan for the PDF version. And here's me with my mentor, Brian. He was such a great help. I don't know if he's here today, but he's a pretty busy person. And beyond the technical knowledge gained during the internship, it was also a valuable networking experience. I connected with many individuals with the intersection of computer science and climate science and engaged in discussions. And while engaging in those discussions, I sought insights into pursuing a PhD for my future. And I was fortunate enough to meet so many students who were pursuing their PhD, and they shared their journey with me. And I was more motivated to pursue a PhD after this experience. Yes, sorry about going over time, but before I end the presentation, I would like to just thank Brian for all the help this summer. His support and guidance throughout this summer has really been instrumental in all that I've achieved. I would also like to thank the CI Compass team, including Eva, Angela, Nicole, and all the other team members in CI Compass, which have made this possible. I still remember when Angela sent out the CI Compass Fellowship newsletter in the School of Science, and I was having double thoughts of whether I should apply, and I just applied last moment, and this has really made me value of taking more opportunities as well. And I would also like to thank Alison Sina for the invaluable feedback and the NCAR admin team. And this is the repo. I think it's still private. I don't know why they haven't made it public yet. And if you want to connect with me on LinkedIn or ask any questions, you can do it here. And I've also journaled the experience. And if you want to just scan this for any notes and stuff, I think it would be really useful. Yeah, thank you for listening.
So next up is Calloway Sutton. Calloway is an incoming third year in computer science from Indiana University, the Bloomington campus. So when you are ready, Calloway.
Sorry, the thing's on the way. So about me. I'm currently a junior, aiming for this MSBS, advanced or accelerated master's program at IU Bloomington in computer science. I'm expecting to graduate in 2025. Some key takeaways from the summer. I definitely excelled in Python this summer, learned a lot. I got to use Golang to optimize a lot of my code in at Hui. And then I got the opportunity to get experience with some actual programmers at Hui, which was fun. I got to play around with Jupyter Hub, machine learning, and I got to learn a lot about different encoding and compression methods. Oh, did I skip over? Yeah, I mean, I was at Hui this summer. Sorry. So I had two main projects at Hui. I worked on the document management system, and then I also worked on the video anomaly detection. Yeah. So the document management system, they had they're using Alfresco 4 at the moment, and it's just kind of outdated. It's unsupported right now. And so we were just looking at alternatives to see, are there any better alternatives in the market right now? And, are there better features that we could get? And yeah, so we found three alternatives. There's just the newer Alfresco 7, and we could just stick to it. Doesn't hurt to just stick with it. There's Mind EDMS. So this is the closest alternative to Alfresco. That's just open source, and it's more of an engine than Alfresco, whereas Alfresco is more of a built solution. Mayan is more like a backend for what would be a built solution, and then GitLab. So it's just a different, instead of going strictly for a document management system, maybe go for a more file management system, since it's just versioning and organizing files. So for GitLab, it was an interesting choice because it kind of fit all the criteria, and it would the only issue is that it would be a huge change in user experience from the way that Alfresco currently handles things. But so a lot of the benefits were that It was like very easy to customize. Little coding was needed to customize it. It allowed for bulk uploads and downloads, which the current system doesn't allow for. It could efficiently like store diff. It could efficiently store the binary files, so like the PDFs and like the different bin files that are stored in Alfresco, using the LFS protocol, which is like built into Git. And then it could, it's more efficient at storing like the version history and author history. And since it uses it uses blob storage, you're not really forced to a certain platform. Like you could, move or self-host your own blob storage. And also like the data is public, but stuff can be restricted. So you don't really need an account to access the data, which was an important feature that we were looking for. But yeah, the user experience thing was like a big downer, so we didn't end up going with it. Then Mayan was a very good choice. It was just that it took a lot of code to customize, so the front end was very hard to make look pretty much. It was probably going to be easier just to make a whole new front end and use the Mayan API and as the back end. It had very good OCR semantic search, but that was only when it worked, and it had some issues with like indexing and yeah. So it just didn't seem ready yet. It's still being built up is what it seems like. So we just kind of ended up going with the newer Alfresco, but it was nice seeing the alternatives in the market and then, just seeing if anything changed. I mean, I think it's always important just seeing the current landscape of the market. But yeah, okay. The second project did was the video anomaly detection with machine learning. So I was asked to try and think of a method for like finding the problem videos that are in the OOI video data set. However, I was also told that there was like a accessibility issue with like the datas with the videos. Like it was hard for researchers to try and actually find the usable data in the data set. So I just kind of tried combining the data into one solution. So basically the problem was like have a means of finding problem videos. Problem videos are kind of subjective. So like what is a problem video? It's any video that wouldn't really be useful to a researcher. So like if the camera dies, for example, or like the light goes out, or just something goes wrong with the camera, or it's just out of view or something. We just need to have some way of like applying a filter and searching for those problem frames. So it's pretty much just having a way to search through the data set in the first place, and then just applying a filter and getting the information. So the theory about how to do it is use a model called ImageNet, which is like a pre-trained image classifying model. And you basically can use that to fingerprint every like second of a video and then store that fingerprint and the timestamp in the video file path, and then just have a way to search for that fingerprint and the similar fingerprints, like by uploading like a image or just some like screenshot or something, and then have a way of returning all of where the similar images are found in the database. So since ImageNet is also built with tokens, it would allow for like simple natural language processing. So like you could, for example, search for like blue, and it would return all the pictures that have the color blue in it. So it allowed for rudimentary like textual search abilities, which might be useful for researchers, or if you need to find like when the camera turned off, look for black, and you get all the frames where the camera's not working. So making the proof of concept, the first step was obviously making like the reverse image search. So I just made a reverse image search by extracting all the videos and all the frames of video into a single folder. And then, I mean, you can easily see like where the problem frames were in this video. It's just this big block of black frames. So yeah, I mean, that pretty much was the solution right there. We could just stop there, but we could also extend it. So we could also group these frames into similar, groups, like cluster them into similar groups, and then extract all the features, or extract the features and then cluster them. And in these groups, then you can search through these groups and return them as like the timestamps. So at this point, I'm able to compress all of these different frames from like 200 kilobytes of information to around 1 to 2 kilobytes of information, which is like the feature vector and timestamp and file path, and store that into a database. So yeah, the potential applications is right now there's 36 million frames, and then around 40,000 frames are added monthly. So that's around like a 50 gigabyte index for searching through this entire 2.2 petabyte video data set, which is very tiny compared to like the whole picture. And then it's around half a gigabyte a year added on to that. So having just a, dedicated service to search through this would last for a couple of years. And this is also using like a relatively simple, so it's using the pickle file format, but using something like protobuf or cap and proto, which are different file formats for storing like this type of information. You could easily save like another 30 to 40% and speed up search times because it's more cache friendly on the CPU. And then the process of analyzing and storing the frame or fingerprints is relatively linear based on the amount of cores you throw at it. So like if you have enough systems, it's just, how much compute can you throw at it, and then how much storage bandwidth can you give it. Yeah. And since the ImageNet, like I said earlier, is based on a set of labels, the labels could be fine-tuned for like the OOI video data set to have like, for example, fine green specks in the bottom left-hand corner, and it would return at least its best guess of what you were trying to achieve or like what you were trying to search for. But yeah, that's like what I was hoping for. And I'm still working on this just in my free time because I think it's just kind of interesting. But the end goal is to have like a web front end where you can just type in or upload an image and do a reverse image search. And I've been messing around with using SvelteKit or Vue with Express with this. But yeah, I've mainly been working on optimizing the indexer at the moment because of just I think I could scale it a lot further, and also just optimizing it would probably be the most helpful thing. But yeah. Any questions?
All right, next up we have Mahee Shah. Mahee is a incoming second year in computer science from the University of Iowa, and she will talk to us about her job at NCAR. Take it away, Mahee.
Okay, so like I was saying, I spent my summer working on machine learning as the center of my internship. So what is machine learning? I bet we're all familiar with ChatGPT, Socratic, Amazon Alexa at this point. And as artificial intelligence becomes increasingly familiar to everybody, we should take some time to learn about a more critical aspect of it, which is machine learning. And it basically underlies the performance and functioning of all our beloved platforms that we use. Machine learning is a subset of artificial intelligence that focuses on creating algorithms capable of learning and improving from data without being explicitly programmed to do so. Instead of relying on fixed instructions, machine learning algorithms use data to identify patterns, make predictions, and perform tasks. These algorithms are created by programmers, but they gain their intelligence through exposure to large data sets. So the training process involves feeding the algorithm with large amounts of data and allowing it to analyze and learn from the patterns and relationships within this data. As the algorithm processes more and more data, it refines its performance and becomes quote unquote smarter in the sense that it can make better decisions or produce more accurate outputs. So machine learning can be seen as a driving force behind many artificial intelligence applications, and it enables these systems to adapt and improve, providing more relevant and helpful responses over time. So why I chose to focus on machine learning this summer stems from my academic background as a computer science major, and I'm minoring in neuroscience. I know these fields may seem unrelated at first, but I think machine learning is the perfect bridge between the two. Neuroscience kind of delves into the understanding of how our brains function and the science behind decision-making processes. Machine learning, on the other hand, applies these fundamental concepts to computers, allowing them to learn from data and make intelligent decisions. The intriguing connection between the inner workings of the brain and capabilities of machines has fascinated me, and actually it even inspired scientists to explore the possibility of creating biological computers. I hope that by immersing myself in the world of machine learning, I can gain insight on how computational models can mimic the complexities of our brains, cognitive processes, and I believe that this will lead to innovative advancements in the future. So, having just completed my freshman year, I'm still exploring lots of different career paths, and artificial intelligence was a very new topic for me. I had very little experience with machine learning when I started my internship this summer, and it left me for a lot of room to learn. To get some background, I started with a machine learning course on Google, which you could see the topics I covered on the left side of the screen. The 6 essential concepts in the life cycle of machine learning that I learned were building AI software using frameworks, training the model, compressing and converting it for efficient deployment, and integrating it into real-world application. So what does this mean? AI software refers to any software application or system that incorporates artificial intelligence techniques to perform specific tasks. These include natural language processing, which I'll delve into more detail later, computer vision, recommendation systems, and more. A framework is a pre-built and organized set of tools, libraries, and components that provide a structure to develop and deploy machine learning models. The 2 learning frameworks I experimented with this summer were TensorFlow and PyTorch. Training a machine learning model, which I briefly touched on in a previous slide, involves using a data set to optimize the model's parameters so that it can make accurate predictions on new unseen data. It learns from the patterns and relationships from the input data to minimize the loss function, or basically error. The more diverse and representative the training data, the better the model can be generalized to new data. Training can involve various techniques such as supervised learning, unsupervised learning, and reinforcement learning. I focused on supervised learning for the sake of my project. Model compression or model compacting is just referring to reducing the size of a trained machine learning model without sacrificing its performance. Converting a model refers to just changing it from one format to another to make it more compatible with different platforms or hardware. And model integration involves embedding a trained machine learning model into a larger software application. So the project I chose to work on this summer, I wasn't assigned any specific project, but to gain a more practical understanding of the concepts that I was learning and working with, I decided to reconstruct an existing project. I chose to look into the natural language processing disaster tweets project. And through careful examination of pre-existing documentation and notebooks, I was able to retrace the steps of this complex problem. This allowed me to comprehensively look at the various components of natural language processing and how they interconnect. So the objective of this project was to classify tweets and basically determine if they were related to natural disasters or metaphoric. So I had access to a data set containing over 10,000 tweets that had already been manually classified as either real disaster or non-disaster tweets. Since this was a natural language processing problem, it's helpful to understand the basics of NLP and how it's used in machine learning. So natural language processing is a branch of artificial intelligence that focuses on enabling computers to understand, interpret, and generate human language. It basically uses techniques combining linguistics, machine learning, and deep learning approaches. And it has a wide range of real-world applications such as Siri, Alexa, translating services, and much more. It continues to advance with ongoing research and development aimed at improving language and understanding and generating capabilities. So the next step was to train the machine learning model. But before doing this, we had to pre-process the text data. This involves tasks like tokenization, which is breaking all the text from the tweet into words and removing stop words, converting text to numerical representations, converting all the text to lowercase, so we can ensure like consistent comparison, and removing words that don't contribute much meaning. So access to pre-existing libraries such as emojis help us with this process. For example, to remove emoji from a tweet, we can simply use the function demojize, and you can see that on the screen. Once this data has been pre-processed, I can select a model to use for text classification. There's a lot of choices. Some common ones are support vector machines or recurrent neural networks. Then to train the model, I split the data set into a training set and a validation set. So the training set you use to train your model, and then and then you use the validation set to evaluate the performance of the training set. Then you can experiment different models and hyperparameters and pre-processing techniques to improve your model's performance over time. And then once you're satisfied with your model's performance, you can use unseen data to see how well it generalizes. The challenges I faced in this project, there were a lot. So like I said, this was already an existing project. There's a lot of different codes and notebooks that show you how to go through it. But one of my personal biggest challenges was picking what I should use to model my project. So since it's a natural language processing problem, it's very common to use GRU. GRU is basically like a smarter version of a traditional computer program, and it works with sequences of data. It's good at understanding like patterns in data over long periods of time. And it basically, you can think of it as having two switches, one for remembering important things and another for deciding what to pay attention to. This helps it avoid forgetting important stuff and getting stuck in important details, which would be helpful in processing tweets. And so it's better at learning from lots of examples. This makes it really helpful for understanding language and predicting future events. However, I ultimately decided to use bidirectional RNNs because of their ability to process input sequences in both forwards and backward directions. This is essential to understand the context of words in tweets in respect to both the content on the left and right. For example, if you consider the following two sentences, I love apple, it's my favorite fruit, and I love apple, I want to work there. We can see that the context on the right of our target word, in this case apple, significantly impacts its definition. So cyber infrastructure and machine learning. Machine learning and cyber infrastructure are very closely intertwined because machine learning techniques and technologies are often applied to enhance various aspects of cyber infrastructure. Some ways in which the techniques I use in my project can help intersect with cyber infrastructure are phishing detection. So machine learning algorithms can learn to identify phishing emails and websites by analyzing content, links, and user behavior to avoid people becoming victim to scams. Malware detection and classification. So machine learning can be applied to analyze malware based on behavior and structural characteristics of it. This helps in identifying and mitigating malware attacks more effectively. And then natural language processing can be used for threat intelligence. So basically NLP techniques can be employed to analyze and understand text data such as security reports, blogs, and social media to gather valuable threat intelligence. These examples highlight how machine learning plays a crucial role in enhancing the security, efficiency, and functionality of cyber infrastructure. And these were the references I used when I was working on my project. And questions.
Okay, so our next presenter is Camila Carvajal. Did I get that right?
Yeah.
Close enough. Sorry about that. Camila is a master's student at USC, and she's been working with Eva Dielman's group. And so with that, take it away, Camila.
So as I was saying, I'll be talking about a soil moisture prediction workflow, which was part of my summer work. I'm a master's student at UT, and during the summer, I worked with maths to translate a workflow that was developed at UT into Pegasus. So the main goals of my internship were to orchestrate SomosPy, which is a machine learning-based earth science workflow with Access Pegasus, and to optimize the workflow to use the resources more efficiently. So a brief overview of SomosPy. SomosPy stands for Soil Moisture Spatial Inference Engine. So it is a workflow for generating gap-free soil moisture data at a finer resolution than available from satellite data. This satellite data has two main shortcomings. For one, it has a coarse resolution of around 27 kilometers by 27 kilometers. And it also has gaps due to snow or ice cover in certain regions, frozen surface, dense vegetation, or other regions. So what SummerSpy does is that it combines this satellite data with high-resolution terrain parameters, which contain information about the roughness of the terrain to provide spatially complete high-resolution soil moisture information. These become useful in applications such as agricultural planning or other hydrology applications. So this is the general pipeline. So we start with a digital elevation model of a particular region of interest. Then we compute the terrain parameters and then combine them into these data sets that are used by the machine learning model. And then we generate the soil moisture predictions at the same resolution at which the terrain parameters are. Since different parts of the pipeline are run at different frequencies, that means like you may generate data one time and then run multiple experiments with the model. Then we separated this into 3 different workflows. And so this is each one of the workflows. I will not go into detail, but this is the general structure of them. We have the input files of green. We have the functions that generate the data, and intermediate files and output files. So why Access Pegasus? So Access Pegasus addresses the need of scientists to execute workflows automatically in heterogeneous environments while preserving portability. And this is very important for reproducibility. So we benefit from this by making SummerSpy readily available to a broader community, and we make our results reproducible. So for those who are unfamiliar, Access is a national cyber infrastructure funded by NSF, and it has a large set of computing, storage, and networking resources throughout the whole country. And it is designed to be used by researchers in different fields. So some of them have limited computing experience, and that's where Access Pegasus comes in. I'm going to show some challenges that we run into while executing this workflow. And some of these challenges became optimizations. So I'll mention a few, and some of the results that I show are using this input data of the Oklahoma region at 10 meters resolution. So we chose this data because it is large enough to raise some memory concerns, but it runs fast enough, like under 11 hours, so we could do like multiple experiments. So within Access, we use Jetstream2 and Anvil as compute sites, and a non-shared file system configuration with S3 storage from OSN. So to start with the challenges, I'll start with the memory, the ones related to memory and disks. So one of them were hard kills on memory intensive jobs. So this was not very straightforward to debug because the job was just killed by the OS without any context or in the error message. So part of the problem was that the libraries we use have poor control over memory usage. So we are working to change some of HD Condor, which is an underlying tool that Pegasus uses to provision resources. So we want to tune the configuration so it, instead of doing a hard kill, it does a soft kill and gives users usable feedback in the error message. So another challenge that comes from memory-intensive jobs is that the memory requirements set the upper limit on how many jobs can run at the same time on a single node. So I'm showing here an example that is from the machine learning prediction workflow. So there's one job in that workflow that uses up a lot of RAM. So for example, for a 3 GB file, it uses around 130 gigabytes of RAM. Which makes parallelization harder. So besides just providing more resources, which is the simplest solution, but that comes at a cost, we can do some transformation-specific optimization, such as modifying the scripts to use lower precision data types or more memory-efficient data structures. So another challenge is that we run into an issue on jobs whose input data size is not constant across all jobs of the same type. So in our case, this happens because a region can have an irregular shape and the tiles are rectangular, such as shown in the figure. So as a first approach, we were requesting memory for every job of the same type based on the worst case, so like the largest input. However, this translates to portions of the requested memory that go unused at runtime when there are smaller inputs than that worst case. So the alternative is to request memory per job, but that comes with added complexity, and we have to do profiling runs to measure the relationship between input size and memory usage. And this ensures that portions of memory do not go unused, and we can run more jobs in parallel. So other types of challenges that we ran into were related to data transfers. So for example, in this particular workflow, the input comes in the form of multiple files downloaded from USGS servers. And so by default, Pegasus downloads first the data to the data staging site, which in our case is OSN, and then it is staged in the compute side. So this additional data transfer is useful when for example, these downloaded files are used by many jobs, but since in this case, it's only used by the first job, then the additional data transfer may increase the runtime by quite a bit. So for our example of Oklahoma, the runtime decrease when we bypass this staging is not that large because of the size of the data, but when we go to a larger region, such as the United States, and the elevation model is heavier, and so we can see a runtime decrease of about an hour by avoiding these additional data transfers. And there are other two optimizations that we have identified, but these are more for future work. We haven't implemented them. So one of them is job clustering. So this is for jobs that, like in the image, they use the same input file. So when they are running parallel in one machine, data gets downloaded multiple times. So you need like the storage space in order to do so. But if you want to limit the data transfers, you can cluster jobs that use the same input together and then treat that as one large job. This takes longer to run, but it reduces data transfers, which, depending on the size of the files, can be very costly. And another possible optimization to eliminate data transfers overall is to run the workflows on our shared file system, which is harder to implement since we're running the workflows inside containers, and it would mean to bind mount the shared file system into the container. And so in conclusion, to maintain portability, some workflow optimizations cannot be tailored to a specific execution environment, and they can be performed either at a transformation level or workflow level to use the resources more efficiently. As I mentioned before, for future work, we could use other optimizations such as clustering or shared file system to eliminate data transfers, and also finding sites where compute is closer to storage. And some takeaways that I learned while working with maths. So from the technical standpoint, it was quite a lot. So in general, about workflow managers, and specifically about Pegasus, debugging workflows, containers, a little bit about OS, which used to be like kind of a black box for me, going through logs, workflow and job level optimizations, georeference, working with georeference files because I had to migrate some of the software, so it was easier to run, which was written by the scientists in R to Python. And skills, something that I valued a lot was to work on partial results, and that way iterate faster rather than wait for a final polished result to present. And so, yeah, that's it from my side. Do you have any questions?
Okay, and so yes, our next speaker is Eddie Mayer. He is an incoming third year in applied math and statistics at the University of Notre Dame, and he'll speak to us about his summer at NCAR. Take it away, Eddie.
Hey everyone, can you see my screen just before I start?
Yes, we can.
Okay, sweet. So just a little about me. So like Nikki just said, I'm a third year student at Notre Dame. And just recently I switched to computer science, but I'm also still applied math, but yeah, I'm computer science now. So I participated in CI Compass this past spring, so spring 23. And like I just said, I added computer science recently. And before CI Compass, I had no experience in programming or computer science. So this was like an awesome opportunity for me. So what is NCAR? I know we've had a few NCAR presenters, but just in case there's still a little confusion. So NCAR stands for the National Center of Atmospheric Research, and they conduct cutting edge research on the Earth science system. Focuses on weather patterns, trends. It studies the air quality and other aspects of the Earth's atmosphere to enhance our understanding and predictability of weather. So NCAR develops and operates advanced scientific instruments and models and data analysis tools to support the global scientific community and decision makers in addressing environmental challenge. So just some background about what I did. So I worked remotely for the software engineering group within the Climate and Global Dynamics lab at NCAR. The host for my visit was Dr. Brian Dobbins, and I was assigned the Neon NCAR project where I looked at software engineering for data visualization and analysis capabilities. And then just to preface, because I was remote, my experience was very different than the other NCAR interns. I mostly observed, and my visit was mostly observational, and I got to attend meetings and seminars with NCAR professionals on the NEAN NCAR team to see what life would be like if I were to pursue a career at NCAR. So with that, opportunities that I took advantage of all summer, the first was the Professional and Development Workshop Series, which was a weekly like seminar session where we got to learn kind of like work environment etiquette and just like communication techniques in like a science foundation, how to enhance your resume, your cover letters, your elevator pitch, all that fun stuff. There were NCAR visitor lunches where you just got to speak to some professionals in the fields, the interns, know everyone. And then my favorite part, the Climate and Global Dynamics seminars, where we heard professionals in the field speak on pressing issues. Climate and Global Dynamics Cafe, similar to the NCAR visitor lunches, and then socials to talk to NCAR employees and interns. So more on opportunities, because I was a visitor who mostly observed throughout my time at NCAR, I got to meet with Brian and talk about topics that truly interested me. So I kind of got to tell Brian what I was fascinated in, what I was interested in. And from there, he would recommend scientific papers, articles, essays, and then we would discuss those together. So some of the skills I learned scientific writing. I got to talk about the intersection of stats, computer science, and data science, which is essentially the two majors I'm pursuing at college. So it's awesome hearing from a professional. And then I also got to talk with Will Weeder about stats. So highlights, I got to read and discuss the scientific paper Overcoming Barriers to Enable Convergence Research by Integrating Ecological and Climate Sciences with Brian and Will Weeder. And just some background, this paper introduces the NCAR Neon system, which is when I said I studied the NCAR Neon project, this is largely what they were working on. So this system is a computer platform connecting ecological and climate sciences for collaborative research. It combines data from Neon's ecosystem observations and NCAR's climate models to enhance model data comparison. The system's user-friendly interface eases access to Neon and NCAR resources, overcoming data and computing barriers. By using Neon's quality data and CTSM simulations, researchers can better understand Earth's changes. The system encourages collaboration among scientists from different fields and bridges ecological and climate research. So kind of like I was saying, I got to discuss like computer science and stats and software engineering with Brian, but I also got to hear like the ecological perspectives from professionals in the fields like Will Weeder. So that was like an opportunity that I would have never had anywhere else. So that was extremely rewarding. And then I also got to, this was super cool. I got to walk through these scientific papers with Brian and kind of see the models they're building and then the code behind the models. So this is just an example of one from the last scientific paper I was talking about. So this graph compares real measurements, which is these orange lines, how much carbon is being released or absorbed by the ecosystem at these two locations here, one in Kansas and Wisconsin, and then the predictions made with the blue line. And then when the orange is above zero, it's releasing carbon. When it's below, it's absorbing carbon. And the blue line shows that prediction. So it was really cool to see how this translates in the real world, especially because this most recent spring, I kind of did something similar at Notre Dame in one of my applied math classes. So it's really cool seeing how like the stuff I'm learning in the classroom translates to a major science foundation. More highlights. This is kind of what I was talking about earlier, but I got to learn how to leverage this opportunity during my future job search. I got to optimize my resume, learn how to create an effective cover letter. I learned interviewing skills and how to give an elevator pitch. And over the 10 weeks, I kind of developed this elevator pitch that I included below, where I just highlight my credentials, I highlight what I did at NCAR and what I hope to do with that experience. So more highlights, I got to attend many seminars from experts in different fields, which was super, super unique. One that particularly stood out was Mark, and I'm totally going to butcher this, but Mutzefeld's seminar. And he kind of just talked about the environmental conditions that influence the occurrence of mesoscale convective systems and their interaction with convection and circulations, which aims to improve parameterization in weather models by implementing a scheme to account for MCS formation under different conditions. He kind of talked about how the study uses a global data set to analyze factors like convective instability and moisture supply, identifying total column water vapor as a key determinant of MCS occurrence. So kind of like I keep saying, I really got a glimpse of many different fields at my time at NCAR by attending these seminars. So it wasn't just solely software engineering, it was learning about ecology and meteorology, which was awesome. Another seminar that was awesome was Veronica Earring's. This was totally up my alley. I absolutely loved this one. It was about machine learning to improve climate change projections, and she addressed biases caused by small-scale phenomena in climate models. Talked about short simulations and how they're employed to develop machine learning-based solutions that mitigate biases. So that was awesome hearing kind of about that machine learning, which is what I'm particularly interested in. So it was cool to see that intersection of kind of ecology and computer science. And then skills that I learned and used throughout my time, I got to enhance my skills in Python and R. And like I said, since I'm new to computer science, these were very necessary advice, tips, strategies. And I got to explore what's it called? Jupyter Notebook. I got to enhance my scientific writing and communication, not only in scientific papers, but I also learned how to write like an effective professional email in a scientific setting. I got to learn how to navigate the application process and how to use data manipulation analysis. I was introduced to NumPy and Pandas. And then Brian also helped me with data visualization and collection techniques by using Matplotlib. So thank you everyone for listening. Thank you NCAR, CI Compass for an amazing spring and opening this door for us and all the fellows. And if anyone has any questions, I'm open to any.
All right, so next up we have Edward Lin, who is, I guess, incoming senior now. Am I correct in that? Eddie has been, he was our CICF fellow in 2022 and actually did a fellowship with us last summer. And so this summer he was able to do some work at NCAR. So Eddie, I will let you take it from here.
Thank you for that introduction. So today I'm going to talk a little bit about what I did over the summer at NCAR. So first I'm going to give a short introduction about my summer and then go into the project that I worked on and then just provide an overall summary of everything that happened over the course of the program. So these are my key takeaways or what I found most valuable over the course of the summer, which was firstly being immersed in a lab setting isn't an opportunity that I've had before. I've worked in labs like in school, but not like full time, just being in a lab around scientists and engineers all the time. And I feel like that was a very cool opportunity for me. And I was able to attend team meetings and sit in and even participate in discussions and offer my own ideas, which I felt was a very valuable experience. And having personal conversations with engineers and scientists and hearing about all the projects they had going on and what they were working on was something that offered me a lot of insight into what I could potentially be doing in the future as well and where I would want my career to head down. And finally, just being able to attend seminars and learning about new topics in science was something that I found very interesting as well. Now onto my project, which was similar to Mahee's, which is also the binary classification of disaster tweets, but I used BERT and PyTorch as my method of classifying these tweets. And just to offer a little overview, the whole idea was to classify tweets relating to natural disasters because Twitter is, or maybe with recent developments, was a way for many people to obtain information. And it's important to separate the relevant information to what's not as relevant, especially when it comes to a topic as, I guess, as important as natural disasters, because that affects people's personal lives and they would need proper information to make the right judgments on how to prepare for a natural disaster, for example. And I worked to create a natural language processing model using PyTorch. And it was an idea to attempt to run this model on a supercomputer at NCAR and analyzing the performance benefits on that. And that sort of links it back to the whole cyber infrastructure aspect of the program. And just to provide a little summary, the three main tasks of this project was to first pre-process the data and then analyze the data to see if that would give some insight into what features would differentiate the two different classes within the data set. And finally, the final task would be to classify tweets. And when it comes to the data pre-processing, the main idea here is to clean up the text data. The tweets came in with, in the data set, had a lot of unnecessary information that isn't relevant to the classifications. For example, URLs, emojis, HTML tags, and like punctuation isn't something you want to look at when coming to classify the tweets. You'd want the specific information and the words. And so URLs, emojis were all taken out. And then the text was tokenized and made lowercase because the case of the text wasn't that relevant either. And words that didn't have as much meaning, such as stop words, were also taken out. And finally, a part of speech tags were applied so that lemmatization could occur to simplify the text even further. And then that was all converted back to its original string or tweet form after being cleaned up to prepare for data analysis. And data analysis was to help gain insight into features of the different classes, even though later on it's a program determining whether or not a tweet is natural disaster related or not. It's useful for us to have some idea of what the program might be looking at and what different aspects of the tweets would provide, what helps separate the two different classes. And one other thing that's important is looking at the distribution of your data set, because you'd ideally want them to be pretty evenly distributed between disaster tweets and non-disaster tweets. And in this case, I think it was about 43% disaster tweets and 57% non-disaster tweets, which was quite close. So that meant that the data was probably viable to be used. And when looking at character lengths, word count, and word lengths, it was revealed that all of them were slightly longer for the disaster tweets. So that may be a differentiating factor between the two classes within the data set. And finally, looking at the most common words that occur within those tweets was something that I felt offered even more ideas as to which tweet would belong at which class, because many of the disaster tweets contain words such as fire or police, or things that you would think would be related to natural disasters. And even though these words occurred in the non-disaster tweets as well, overall, non-disaster tweets contained a much greater variety of words, and there were no words that stood out as much other than the typical words you would see in many sentences, such as like at, I'm, those words. But for disaster tweets, it was disaster-related words that occurred most frequently. And for classification, I chose BERT because which stands for bidirectional encoder representation of transformers, because it's this machine learning model for language processing that's probably the most used right now, or at the forefront of natural language processing. And once again, for this, the text needed to be pre-processed as well, but in a certain way, which also involved tokenization and lower casing, but special character, because the BERT model required special character tokens to be inserted into the text data, such as tokens that identified where the beginning of sequences, or in this case, the beginning of a tweet is, or separating tokens to separate the different tweets, as well as padding sequences, because you'd want every tweet to be the same length. And from that, a attention mask was also required, because padding tokens aren't something you really want to look at because it's padding and it doesn't really have any meaning. So an attention mask would tell you, oh, this is a token from the original tweet that the model wants to look at this, or this is a padding token. It's not that useful. The model doesn't want to look at this. So that was used. And finally, a batch size of 32 was used. And I think in the BERT paper, it was recommended either 16 or 32. And I think just based on testing, 32 seemed to most likely produce better results. And when it comes to setting up the model, it was mostly done through PyTorch with their BERT large uncased model, and with two classification labels being disaster or non-disaster. And finally, most of the hyperparameters were first set up based on recommendations in the BERT paper as well. And finally, training and evaluation was done once everything was set up. As for the accuracy, it often hovered around 80%. And because the data sets aren't that large and relatively small, with performance may decrease even further, or I'm hypothesizing that the performance may decrease even further with more unseen data. So improvements can definitely be made here. So some next steps may be to tweak the hyperparameters even further, because right now most of them are around the recommended value. So maybe through more testing, the accuracy could be brought further up, and other models, natural language processing models, could be looked at as well that might work better for this particular use case. And finally, I never got around to doing this, but running the model on a supercomputer and measuring the improvement in performance is also something I would be interested in trying. And finally, just to offer a summary of my summer, I felt that this was a very unique learning experience for me. Working in a research lab isn't something that I've ever done before, and being immersed in that environment was a very valuable experience to me. And there are many aspects of this program that I found helpful, even though my presentation centered around mostly my project. But attending the seminars, getting to talk to scientists and engineers were all things that I really enjoyed. And finally, just visiting the city of Boulder was something that I never really thought I was going to do, but I visited, and it was a very nice experience, and it was great to visit. I might even go back sometime. And thank you for listening to my presentation.
Our next presenter, unfortunately, is unable to make it today. Bhagya Oram is an incoming second year in data science at UCSD. However, she has provided us with a recording of her presentation.
Hi, good morning or afternoon, wherever you're watching this from. My name is Bhagya, and I interned at the National Center for Atmospheric Research this past summer. I really wish I could be at the CI Campus Summer Symposium right now. I'd love to hear all the other presenters. But when you're watching this, I'm likely going to be in a flight from LA to Singapore. I'd like to thank Nikki and Angela for giving me the opportunity to submit a pre-recorded presentation. I just completed my freshman year at UC San Diego as a data science major. I'm very interested in exploring the ethics behind machine learning and data science, and also exploring the intersection of tech in a bunch of different industries. I took part in the CI Campus Student Fellowship from Jan through April of this year. It was an incredible learning experience, and I learned about the data lifecycle and cloud computing. I also learned the best practices in software development and data analysis. All of these skills proved to be incredibly helpful when I interned at NCAR this past summer. Here you can see screenshots of my group and I's presentation on the last day of the student fellowship. We chose to study the data acquisition and the data practicing methods of the Cornell High Energy Synchrotron source. The screenshot below is one of me presenting the data flow of the lab's data acquisition system. When it was time to indicate our top choices for NSF major facilities to intern at, NCAR was among my top choices. I've always wanted to explore scientific computing. Ever since I took a class on climate justice in the fall quarter of my freshman year, I've been interested in climate change studies and understanding how the atmosphere operates. As you can imagine, I was very excited when I learned that I was going to be interning at NCAR. At NCAR, I worked at the Atmosphere Chemistry Observations and Modeling Lab, or ACOM. ACOM's research is organized around two major themes: air quality predictions and weather chemistry climate interactions. ACOM developed a community modeling infrastructure called MUSICA. MUSICA stands for the multi-scale infrastructure for chemistry and aerosols. This is a computationally feasible global model that is used for the simulation of large-scale atmospheric phenomena. One of the most important projects of Musica is called Music Box, which is a project that I interned with. On this page, you can see two screenshots of NCAR. NCAR's primary location is in Boulder, Colorado. It's an absolutely beautiful location. So Music Box, the project that I interned at, is a computer model that's used for exploring the sensitivity of atmospheric chemistry to various parameters. It simulates the chemistry and the transport of trace gases and aerosols in the atmosphere. This is a model that is widely used in the atmospheric chemistry and research community, and it's also used in classrooms. Professors frequently use the Music Box model in its interactive configuration to generate publicly available model exercises and to validate the box model results. A box model in its simplest form is something that allows scientists to study the interactions between various chemical reactions in a literal box that is placed over some location on the planet. This image that you see right below the heading it explains the physics behind a box model. I worked primarily on the front end of Music Box. As you know, the front end and the back end interact and communicate with each other using an API or a library. Through working on the front end of Music Box, I gained hands-on experience with React and Redux, which are both extensively used JavaScript libraries. React is used for creating separate components that can easily be reused in any project compatible with React-based code. This accelerates the development process because you're essentially reusing several bits of code. Redux allows you to manage your app state in a single place, and it keeps changes in your application more predictable and traceable. I spent the first few weeks of my internship getting accustomed to these technologies, while also getting familiarized with Fortran, in which a significant portion of the model was coded. I would get assigned bugs in the interactive client portion of Music Box, and to solve these bugs, I would first try to reproduce the bug in its local state. A lot of the time that meant running the model on NCAR's VPN and understanding what exactly the error message was. Next, I would go through the commit history on the GitHub. You can see a screenshot of Music Box's GitHub here. I worked specifically on the repo of the interactive client portion of Music Box. So anytime I was assigned a bug, I would go through the commit history to see if there was a recent change made to the code that somehow triggered the bug. Next, I would aim to isolate the issue. This was essentially so I could really understand what specific part of the code was causing the issue. So I would do this with the help of print and return statements. I would make sure that I had a thorough understanding of the bug that I was dealing with. And to do this, I would review documentation, and I would reach out to colleagues and fellow interns also working on the Music Box model in order to better understand what the code was trying to achieve. I honestly love how collaborative the entire process was, because I truly believe that fresh perspectives can often lead to breakthroughs. Through this internship, I got to experience stand-up meetings, which were an incredible opportunity to meet the rest of the team and understanding what everyone else was working on. Spending a summer with NCAR was a great experience, and one that really helped shape my perspective on both high-performance computing and the intersection of science and technology. I realized that I love working in interdisciplinary teams where everyone has voice and everyone's needs are taken into consideration. It was inspiring to hear the different perspectives of staff scientists, programmers, and academics, and to see how we could pool our expertise to tackle complex problems. the opportunity to improve our understanding of our atmosphere, that is an incredibly profound impact to have an impact on such a large scale. I believe is one that is unique to the atmospheric science community. I'm excited to seek work experiences that continue to challenge me, open my eyes to new perspectives, and ultimately have a positive impact. As I wrap up, I would absolutely love to give some shout outs to the amazing people that have helped me get to this position. First off, I'd like to thank Nicole Verdone and Angela Murillo. I first met them at the beginning of the student fellowship in January, and the two of them have been absolutely incredible. They are positive, enthusiastic, and dedicated. They helped me see the importance of collaboration and communication, and I would forever be grateful to them for putting me in touch with NCAR and for helping me get this opportunity, and because I've gained some incredible experience from this. Next, I'd like to thank Brian Dobbins, who was my mentor at NCAR and who Nicole and Angela actually introduced me to. Brian introduced me to NCAR, to the project I was going to be working with, and to both of my amazing team leads. He was no short of an amazing mentor. He is incredibly enthusiastic and was receptive to me throughout the internship, answering absolutely any and all of my questions. He made it very clear that this internship was primarily a learning opportunity, and that I should treat this as a way to figure out what avenues in technology I'd like to explore further. And I'm absolutely grateful to him because he is one of the reasons that I'm now considering working in scientific computing as a full-time career. Next, I'd like to thank Matt Dawson and Kyle Shores. Both of them were the team leads on MusicBox. They were incredibly helpful throughout and provided a high level of support to me. Through the internship, they were always available if I needed any help, whether that was with figuring out what version of a particular package I had to install, or jumping on a call to figure out or to understand a bug further. The two of them were always there for me, and they were amazing managers to have through this process. Lastly, I just like to thank the CI campus community, because if not for my student fellowship, I would likely have never considered working in the intersection of science and technology, even though both of these are areas that I'm so fascinated by. And I'll be forever thankful to have met this amazing community and to have gotten this opportunity. If you have any feedback on my presentation, or you would just like to reach out to talk more about scientific computing or atmospheric science or anything really, please feel free to reach out. That's my UCSC email right there. And feel free to connect with me on LinkedIn as well. Thank you so much for this opportunity. I hope everyone has a great rest of your days, and thank you for your time today.
Okay, we did it.
If I may just jump in and use my prerogative to thank all the CI Campus Fellows. You're just awesome and very inspiring, and we love working with you. I also would like to thank our major facilities host, so Jeffrey, and unfortunately Brian cannot be with us. I believe he's under the weather, but thank you so much for these great opportunities for the students, and we'll look forward to working with you next year, so don't go anyway. And also David from MagLab joined us as well, and he was one of the guest speakers and a big participant in our CI Campus Spring program. So thank you, David, for attending today. Kevin, you're sending us the money. Thank you for that. You can see it's well spent. And big shout out to the CI Campus team, in particular, Nicole, Angela, Eric, and Dawn for working with the students, making this program happen, and really putting all your heart and into this. It really shows. And thank you all so much.
And our excellent TA Sarwar. Thank you.
Yes, sorry. Thank you. I thank you so much for all your work and all the emails that you send and keeping everybody on track and working with the students. Thank you, Sarah. Thank you.
All right, with that, I can stick on if anyone has any other questions, but with that, thank you very much to everyone and have a great rest of your day.